So we're going to finish section 4.1 about divisibility. We have a whole bunch of divisibility rules. We have properties that talk about when certain pieces are divisible, how we decide if they're sum or difference are divisible. And we were at the point where we had looked at example 5 and created the numbers that work in this one, and we're on example 6. So example 6 asks us to answer the following and justify our answer. So if a number is divisible by 5, can it be divisible by 10? Sometimes. So can it? Yes. So the key word here is the word can. So can it? Yes. And since it's a can, it's not saying it has to do it all the time. You can give an example if it helps. Yes. So give me an example. Sure. So for example, 5 divides 20. Remember that notation from last time, that vertical bar? 5 divides 20. And 10 divides 20. But then it has sort of a follow-up question within the same thing. Must. Must it work? No. So Justin, you got the floor. Not always. It's kind of like answer I and answer double I. Can you give me an example?
25.
Sure. For example, 5 divides 25. It does. But 10 does not divide 25. Right? Okay. So now we're going to change the question to be the reverse. Okay. If a number is divisible by 10, can it be divisible by 5? Yes. So again, can it just means like showing an example of one that works. So can it? Yes. For example, what? So we have to start with something divisible by 10 now. 30. So 10 divides 30, and 5 divides 30. The second question, must it? The answer is yes. So on this one where we say yes in the affirmative that it always works, we can't just justify with an example because it has to work for every example, and I can't show every example, so we need to justify it some other way. So why does it have to be true all the time?
If a number is divisible by 10, then it has to end in a 0, which automatically makes it divisible by 5, because numbers that are divisible by 5 end in 0.
Perfect. Number divisible by 10 ends in 0. And all numbers ending in 0 are divisible by 5. Does that make sense to everyone? More importantly, do you understand why we can't justify it with an example, whereas we could on the other 3 parts? Okay. So anytime we're trying to say something must be true and it has to work all the time, the justification cannot be with an example. It has to be more broadly discussed. Okay, fabulous. All right, one more question, and then we're going to take a look at an interesting thing that we peeked in briefly last time, and then we're going to just explore a little bit more fully. A number in which each digit except 0 appears exactly 3 times is divisible by 3. For example, 777,555,222 and 414,143,313 are divisible by 3. Okay, so every number that's showing up in there, except for 0, if it showed up and doesn't in these, shows up 3 times. So everybody see those? Why in the world would that be enough to know for sure that the number is divisible by 3?
If you add that by 3, then it's divisible by 3. So 7 plus 7 plus 7 is 21, and that's divisible by 3. 5 plus 5 plus 5 is 15. That's divisible by 3. 2 plus 2 plus 2 is 6, and that's divisible by 3.
Okay, so I'm going to use just 3 arbitrary letters because we're trying to explain why it always works. So if I have 3 letters, right? 3 numbers added together, A. This would equal 3A, and 3 will divide 3A for any A, right? So if A is 7, if A is 5, if A is 1, 0 doesn't matter. That was the description they talked about before, because 0 doesn't add any values to anything. So we could have some arbitrary zeros showing up in here and it wouldn't change anything. But yeah, and so every value, every digit, let me say that, every digit in our number has this property. So the sum divides by 3, making our value divisible by 3. Okay, so if it has this property, it was definitely divisible by 3. Does this statement have to be true in order for a number to be divisible by 3? No. And anytime you're trying to prove something's not true, an example will work. Can you give me an example of a number that doesn't look like one of these, but it's still divisible by 3? 18. I was like, don't go thinking too big. 18 works just fine. 18 does not look like 3 numbers repeated a bunch of times, right? Like, that's not what's happening here. And 3 divides 18. But it doesn't have this property. Okay, are you ready for something interesting? Okay, so let me remind you where it is we're getting this interesting piece from. It has to do with divisibility by 6. So divisibility test for 6, this stuff at the bottom is divisibility test for 11. So let me just delete it so we're not distracted by it. We're looking at this piece at the bottom, the divisibility test by 6. So the divisibility test for 6 feels like it makes perfect sense. 6 is 2 times 3, so if it's divisible by 2 and 3, it's divisible by 6. If it's divisible by 6, it's divisible by 2 and 3. And in fact, we had this example over here, example 2, parts A and B, that we actually said that it's true. It works both directions, it's all good. But then we had this weird thing happen on C and D where it worked one way, right? I could break 8 down into 2 and 4, and it worked, but just knowing that it was divisible by 2 and 4 did not make it divisible by 8 necessarily. Sometimes it would, but it wouldn't have to. So we're going to try and figure out what is it this special about the number 6 that 8 doesn't have that makes 6 do this when 8 fails. So we're going to do this by me giving you a list of things that work and things that don't work. And you're going to try and figure out what is in common to the things that work that is not in common to the things that don't work. And we already have one example and one non-example for our list. So these are my examples on the left of things that work. And then I'm going to have non-examples on the right. Now, your goal once you think you've had it, though, is not, like you're working in your pair or in your group, whatever, is not to spoil the fun for the other group who's still thinking. Once you think you have it, I want you to give me what you think is either an example or a non-example, and if you're right, I'll put it on the list where it belongs. If not, I'll put it on the other list, and you get to keep thinking. So we've already said that an example of one that works is 6, and we considered the numbers 2 and 3. And an example of one that didn't work was the number 8, and we considered the numbers 2 and 4, I think was what we had, right? Okay, so I'm going to give you some more examples and non-examples, and we're going to try and figure out what is it that the examples have in common that the non-examples fail to have that piece in common. So I'll do 15. We'll do we have 16 would be fine. We'll do 16. You could do 16 with that one. Oh, that's better. We'll do it that way. You can do 12 with 3 and 4, but 12 fails with 2 and 6. You do 35 with 5 and 7. You can do 36 with 4 and 9, but 36 would fail with 3 and 12. Okay, so every pair of numbers or every number I'm giving you, the values that are up after it multiply to be it, right? Like that's a feature that everything has left on both sides of the things. What we're trying to figure out is why does it work on the ones that are the examples and why is it not working on the ones that are not the examples? So chat with each other and see if you can figure out what it is that they have in common. And I'll keep adding to the list as I think of random other numbers. 24 is one we can use. Done this enough times that I realize some of the misconceptions. I try to create examples that won't lead to those. I try. Can I give you a hint? What you need to be looking at is the kind of numbers and their relationships. I shouldn't draw it like that. Between the two numbers compared to the relationships between these pairs of numbers. within each pair. There's something special about the relationship within each pair that either makes it work or not work. Do you think you know what it is? If you think you know what it is, add a number to my list somewhere.
I don't want to be told because I want to do it. It's like, don't say anything.
Give me an example. What do you think, Addie?
An example?
Yeah, where do you an example or non-example, either way.
I think an example might be 40
Okay.
and then 9 and 5.
You mean 8 and 5?
Yeah, that's what I meant.
Yep, that's an example. Can you break 40 apart differently that doesn't make it work?
10 and 4.
Yep.
Ah, I didn't get it.
Yeah. Oh! Oh, I want to get it so bad. Yeah, that makes sense.
I'm going to add something, Jane Ellen.
Yeah, I'm trying to think of another.
Think of another one
example
for
or
me.
non-example, yeah.
Okay. And it doesn't have to be in both sides. Like
Oh,
some of
okay.
my
I
numbers
was
do,
thinking, I was like,
but not all of them did, right? Like 6 is just in one category, you know, so it doesn't have to fit in both categories, but it might.
Yeah, wait. No.
It's not easier coming up with it. If we got it right, it's easier coming up with examples
Yeah.
than non-examples.
Yeah.
Maybe. Maybe not. I don't know.
My example list is longer than my non-example list, so one could potentially argue that, yeah. So let's think about these numbers on the right side and these pairs of numbers. We can go down that red list and circle them all, but so you take a look at each of these pairs of numbers. They all have something in common. What do 2 and 4 have in common? They're even. And they work that way all the way down.
Except for the 3s.
Except for the 3 and the 6. So what do 3 and 6 have in common? Hmm?
Factors, double,
You had a key word there, Rylan, that's really important. Do you know what the word was you said?
factor.
Yeah.
Mm-hmm.
It isn't about being even, it's about having a common factor. So look at all those orange numbers over there on the right-hand side. every pair of numbers shares a common factor, don't they? But what about my numbers over here in red? Do they share any common factors except for one? Nope. None of them do. It's all about whether the numbers we break them down into have a factor in common. Right? 2 and 4 have a factor of 2. 3 and 12 have a factor of 3. That actually was an odd one as well. 4 and 6, they're not doubles of each other like some of them are, right? But they still share a factor of 2. Same as the 10 and the 4. They share a factor of 2. But all the numbers on the right-hand side that are examples don't have that feature. They have no common factors. And we'll encounter a phrase, I can't remember if it's in 4.2 or in 4.3. We actually call these numbers all highlighted in red relatively prime because between the two of them, they don't have a common factor. It's a phrase relatively prime. And we'll see that coming up. So we can always do this rule of sixes if we can break something down into two factors that share no common factors. And some numbers you can do that with and some numbers you can't, right? Right, like the number 8. There's no way to break 8 down into two numbers that share no common factors unless it's 1 and 8 and then you didn't really break it apart. It's just the same thing it was already. Right? There's no way to do that with the number 8. But some numbers like 12, there's a way to do it that works and a way to do it that doesn't work because they share common factors when you do 2 and 6, but 3 and 4 don't share any common factors. Okay? All right.